Why should we test for normality? Well, if you don't, you might end up making the wrong conclusion. And if you make the wrong conclusion, then you could have a type 1 error or a type 2 error. You could either have a false positive or a false negative, and the consequences are pretty severe. If you are working with microbiological data and you didn't test for normality, you just moved on to the next 4 steps of hypothesis testing, and you said, well, this lot is safe. We can eat it. We can send it to our customers. But you use the wrong test, you might actually have a mistake where it's not safe to eat. So that consequence is pretty severe. On the other hand, what if you told your company that, sorry, we can't ship that, we're going to put it on hold, I don't think it's safe. But on the other hand, it actually was. You're going, oh, geez, man, that's a big mistake. That's a big money-costing mistake. So that's why we care about testing for normality. So, but with that said, if you're working with a set that's not normally distributed, there are some of these tests that are more robust to that, where, in other words, it doesn't really matter whether you use the parametric test for the normally distributed data versus the non-parametric. It is not really going to matter whether you run the parametric or the non-parametric test. And those are going to be the ones where you're concerned about the means and the averages. So a t-test on a mean, we'll talk about ANOVAs and regressions. If you're concerned about the mean, and a good way to illustrate why this is so is, like, let's say you have 2 distributions and you're wanting to compare them, and they're both skewed to the right, and you're only concerned about the means, then the way the math works, it usually is not really going to matter whether you use the parametric test or the non-parametric test. Whereas, on the other hand, if you were concerned about the variance and you wanted to know, does this one have more variance than this one? Then it really is going to matter whether you pick the right test based on whether it's normally distributed. So the tests that are not robust to normality are, like I said, the ones where we're concerned about variance. CPK, that makes sense, right? Because now that you know that one's concerned about how wide, where the car is in relation to the garage, well, now we're talking about not the means, we're talking about the dispersion of it. We'll get into these 2 concepts later on this semester. So what if my data is not normal and I need to analyze the tails? Well, we can either use the non-parametric test, or it's outside the scope of this class, but I'm just trying to give you that 50,000 square foot view so that maybe if you go on and you're curious, this will start to make sense. It wasn't obvious to me until I started teaching this class that sometimes you'll have a set that's not normally distributed. It's widely skewed to the right or something like that. And what statisticians will do is they'll say, okay, well, I don't want to apply the non-parametric test. I can't do the Mann-Whitney on my computer. I just don't like that one. I have a bad history with it. So what I'm going to do instead is I'm going to transform this data so that it looks like a very nice bell-shaped curve and it is normally distributed. And then I'm going to run a t-test, a parametric test. So what you're doing there is you're going from a scenario where you should have been using the non-parametric test because it's not normally distributed, and you just said, this data is mine. I'm going to make you parametric so I can do the t-test because that's the one that I'd like to do. So you'll see statisticians, and you'll see on your computer the option to transform data. And there's different algorithms and a bunch of graduate level statistics classes that will teach you how to do all those transformations if you're interested. Okay, but you know what a normal distribution looks like, right? The mean is the same as the median and the same as the mode. And most of our variable data, like weights and pHs and things like that, is going to be normally distributed. But what we're going to do for normal distributions is we're going to be looking at these tables. So what we've got to do is we've got to convert our data to a Z table, okay? And the data under this curve all equals 1. The idea is that we're going to look up on the table what Z is based on the alpha level, and we're going to calculate what the Z is. We're going to compare those two. I've got some slides that illustrate this. The normal curve, mean, and standard deviation are interrelated. Normal distribution fully defined by population, mean, and standard deviation. This should be familiar based on that second week of class when we were looking at standard deviation. 68% of the data is plus or minus within 1 sigma, 1 standard deviation. Okay.